Welcome back, everyone. This is our second lecture that is going to focus on the bivariate descriptive statistics and specifically examining the association between two quantitative variables. In the first lecture that we introduced you to Pearson's R. Pearson's R, otherwise known as the zero order correlation coefficient, or just the bivariate correlation coefficient. It goes by multiple names, but Pearson's R, we came to realize, was the key statistic that shows us the statistical association between two quantitative variables. We also talked about several of the properties associated with R. We talked about the fact that it has a limited range of values, from -1 up to +1. We talked about the fact that R, the sign of R, tells us the type of association. R values that are negative are indicative of negative associations. R values that are positive are indicative of positive associations. We also talked about the strength of association. The closer that your R statistic is to either -1 or +1 is a sign of a stronger association, whereas R values that are closer to 0 are indicative of weak or no association between two variables. We mentioned the fact that R only measures the linear association between two variables. And that's where our graphical display, the scatter plot, came into play. And you may recall when we looked at the scatter plots, a researcher, or with your eye, with that visual test, you're trying to figure out what is the best straight sloped line, either a positive slope or a negative slope, that you could draw to sort of summarize the association between the X and Y variables. Well, in this lecture, we're going to go a little bit deeper. Now that we've broken down what the R statistic is, how we measure correlation, we're going to start first with discussing a few of the factors that may sort of give us either a misleading value of R. And so why it's so important to not just trust the R statistic, but also to look at a scatter plot prior to finishing our analysis. We're then going to move on to what is known as our first measure of strength of association, or an effect size measure. And this is going to be referred to as R squared. A fancier term that you'll hear will be the coefficient of determination. And we'll talk about how to compute it, how to interpret it. And then finally, we'll finish off briefly with a slide that will show us that even though our focus in this course is to understand Pearson's R, there are quite a few other measures of correlation when your two variables may not both be quantitative variables at that interval ratio level of measurement. Now, the readings for this are just continuing on from what we saw of part 1 of this lecture. So it's still chapter 9 with those pages that are listed. All right, let's go ahead and start talking about the factors influencing the size of R. So we're going to talk about 4 different factors that can give us sort of a false impression about R, or a false or a misleading value of R, I guess I should say. And so the first thing that can happen is we have to make sure that we understand the nature of the relationship between the variables. And what I mean by this is one of the things that I've spoken to multiple times. R only captures a linear relationship. And we're going to talk about what happens when we deviate from that. The second thing is what happens when one of our particular variables, just given on the sample that we're looking at, what if we have a restricted range of values? And then number 3 is what if we have sort of the opposite? What if we have a discontinuous distribution for the range of values for one of the variables? So points 2 and 3 on this slide, you're going to notice when we get there, these have a lot to deal with what the nature of the sample that we're working with, what that sample look like. Are we sort of have like a limited range of the age range of people that we're studying, or some other factor? Or do we have a discontinuous distribution? Do we only have in our sample people who are really low on some sort of scale and high, but we're missing the middle ground? And we'll see how that may falsely influence our values of R. And then finally, once again, sort of a research methods issue, is what happens when, however, we're collecting our measurements for our variables, what if we have poor reliability? And how does that potentially lead to a misleading value of R? So let's spend a little bit of time looking at each four of these factors. So the first factor that can falsely influence the size of R is when we deviate from a linear relationship. So what we see here, and this slide is going to be very similar to what we're going to see on the next few slides. So what you will see is a description at the top. So that's where we see number 1, nature of the relationship, etc. And then at the bottom, we're going to see 2 corresponding scatter plots. And then you'll have it up in the description, you'll see like the left side linear, right side curvilinear. And hopefully these will help us to sort of illustrate and better understand how these 4 different factors can sort of give us misleading values of R. So let's break this one down. So R, in and of, by definition, captures linear relationships. We are trying to draw the best straight line to summarize the nature of the relationship between variables x and y. So let's look at the left-hand scatter plot. On that left-hand scatter plot, we see a pretty nice positive linear shape to that cluster of dots, right? So we can say that looks like a pretty good positive association. It's definitely, if we had to draw a straight line, we could summarize what we're seeing on that left-hand side without much problem. And that's a good nature. That's a linear relationship, and the value that we would get for R would be an accurate reflection of the type and strength of relationship between those 2 variables. But let's now transition over to that right-hand side. That right-hand side, we notice, we look at those cluster of dots, and there's clearly an association, right? Thinking back to our last lecture, this isn't like that no association picture we saw where it was just sort of like a scatter shot or just like a cloud of dots. There clearly is a shape in that right-hand side scatter plot, and it's what we would call a curvilinear association. Now, is this an odd thing to experience when collecting data in real-world settings? No, it's not. A lot of things have this type of curvilinear relationship. For example, let's imagine that variable x, so along that x-axis, was age. So, and we had everything in our sample from very young individuals up to elderly, older individuals, and along that x-axis. And let's say that our y-axis, our second variable, was strength. And maybe we measured strength of being able to perform some feat in pounds or whatever it is. Well, you can imagine that we might expect to see a scatter plot that looks a lot like this if we were looking at the association between age and strength. Whereas when you're really young, low values of x, you're not going to be that strong. But as you get older and the values of x increase, so does your strength, the values of your y variable. But eventually, we hit a certain point in life where our strength will naturally start to deteriorate. And that's where we see sort of the top of that curve or the top of that rainbow shape, where all of a sudden the nature of the relationship changes. So even though this is a real possibility in the world of statistics, if we had data that looked like that right-hand side scatter plot, if we hadn't looked at the scatter plot in the first place to discover this curvilinear relationship, and if instead we had just simply asked SPSS to compute the Pearson's R for that particular relationship, we would get an R value that would be closer to 0, meaning a low or small or weak magnitude association, than we should have, because of the fact that it was a curvilinear relationship as opposed to a linear one. So what we see here is one of the notes I have is that variables that have this type of curvilinear relationship will produce an artificially low magnitude R value. So I say artificially because there's clearly an association, but it's just not able to be captured with R. So if somebody would say, well, how do I capture it? Well, you can imagine looking at that right-hand side scatter plot, if you took your data and sort of split it in two, right where that peak of that rainbow or the peak of that curve occurs along the X variables, if you split your data set into two and you ran a R simply for the left-hand side of that little scatter plot, where there's an upwards positive slope, you would get a pretty accurate R value. And then if you ran a separate R for this second half of the data, the half that looks more like a pretty solid negative slope, you would get a pretty accurate R value, and then you could better describe what you're seeing. And this is one of the key things that for each one of these factors influencing the size of R that I want to stress. Not that they're necessarily a problem, but there's something that you need to be aware of. And it's why it's so important to look at things like graphical displays, like scatter plots, as well as running the actual statistics themselves. Because sometimes you need to see a little bit more with a qualitative eye what's going on beyond simply trusting your statistics. Our second of the four factors that can sort of give a misleading or false value of R is when we have what is known as a truncated or restricted range for one of the variables. So let's take a look. Let's start with our scatter plots down at the bottom. On the left-hand side, let's just focus on the range of values for variable X. So remember, variable X is that sort of that horizontal axis. So we see going from left to right, we notice that we have low X values, medium X values, and high X values. So we have a pretty good range of values for variable X. And sure enough, when we contrast those with their corresponding values of Y, we get that nice looking positive slope. And we would probably expect to get a pretty strong positive R value to reflect that positive linear association in the left-hand scatter plot. But now let's look at the right-hand scatter plot. And as you can see, there's a lot fewer dots. And what I've done here is it's still the exact same type of relationship between variable X and variable Y, but what I have removed from this scatter plot are the observations or the cases that had low values of X. So there's four of them. So if you sort of match the dots in the left and right hand side, you'll notice at the far extreme left hand side, there are four dots that are there in the left hand scatter plot, but are not there in the right hand scatter plot. So this would be an example of, let's say that if the X variable was age, let's say for some reason we did not happen to get into our sample people below a certain age. So maybe I have a limited age of range, or limited range of age, sorry. And then on the upper hand, I also have it limited on the upper values of X. So the same idea, if you look at sort of contrasting and comparing the two scatter plots, there are, let's see, 1, 2, 3, 4, 5 of the higher values of X that exist in the left-hand side scatter plot, but they're not there in that right-hand side one. So maybe, and this happens a lot in research, you go out and you collect data, and just given by the sample, maybe if my variable X was age, maybe I don't get very many young individuals in my sample, so I'm limited in that. And I also don't get very many older individuals in my sample. And so what is left is only sort of that middle block. So when we look at that right-hand scatter plot, I get a sample of data of a bunch of people that are sort of like in a very constricted or truncated range of age for variable X. Now, what does that do to my R coefficient, my R statistic? Well, what happens is, if you try to draw a line, and just visually it should make sense, hopefully you get the idea that trying to draw a nice line with a positive slope to summarize the nature of the relationship in the right-hand scatter plot is not going to be as easy or clear-cut as it is in the left-hand one. So what happens when we actually get the statistic produced, if one of the variables has a restricted range, what we see in the right-hand side, we will get an artificially low magnitude value of R. So once again, artificially low magnitude simply means an R value that is closer to zero than it really should be if we had access to a full range of values in our sample. So sort of the opposite of that restricted range that we saw for factor number 2 is when we have a discontinuous distribution. And this is a similar idea. Discontinuous distributions simply means that for one of the variables that we're measuring, we just don't happen to get in our sample the full range of values that we would like to see. So whereas a truncated range on the previous slide may occur when you're only able to sample people, say, like a limited demographic or a limited age or a limited intelligence level, whatever one of your key variables is, you're limited. A discontinuous distribution might occur when you select your sample, and maybe one of the criteria for selecting your sample was looking for people who scored really low on some sort of measurement and also people who scored really high. And so what you end up missing out on are all the people in the middle. And so that's what we see with a discontinuous distribution. So let's take a look and figure out how that can falsely or misleadingly influence our value of R. So in the left-hand scatter plot, what we see is, once again, we see a good range of values from low to high X, as well as, in looking at the Y-axis, values that are from low to high Y. And when we think about trying to draw a good sloped straight line to summarize the cluster of dots we see on the left-hand side, we may go, okay, it looks like a positive association, but the dots are not going to cluster very tightly around that line, and therefore the magnitude of R isn't going to be all that big. But let's imagine what happens if we look at the exact same sort of overall sample, but we're missing the middle people. And that's what we see in the right-hand side scatter plot. So just like I did with the other one, all I did was remove a handful of observations. So let's say when in the course of collecting our study, we end up with a sample that looks like the right-hand side, where we have people who were on the lower range of X values, and they're included. And we also have people who are on the very upper end of X values, and they're included. But the people who were in the middle, for whatever reason, they weren't part of our study. Maybe it was part of how we designed our sampling approach. Maybe it was because we were sampling people with a certain sort of specific focus. But for whatever reason, we end up with this sort of discontinuous distribution. Well, how does that influence R? Well, think back to yourself once again. Imagine drawing a straight sloped line to summarize those points. On the right-hand side, we could draw a line that would start down in the cluster on the lower left, and then would go up and cut through the 3-point cluster in the upper right. And even though there's a big gap in between those two areas, R doesn't care. That's not part of the mathematics of it. It's simply going to say, given the observations that were provided to me, which in that right-hand side is what, 1, 2, 3, 4, 5, 6, 7, 8 different points. It's going to say, what is the best line to summarize those? And then also, how tightly do each one of those 8 points cluster about that line? So on that right-hand side, even though there's that big gap in the middle, you can imagine that the R is actually going to be artificially inflated. The magnitude of R is going to be higher than it should because there's not as much of sort of like the cloud or the spacing between the line and the actual observations. Whereas on the left, we look at that sort of middle section of values, and those, once we try to draw a straight line, they're going to be much further. The cloud is going to be bigger. They're going to be further away from the line, which is going to reduce our value of R. So the takeaway from this is this. If one of the variables has a discontinuous range, like what we see on the right-hand scatter plot, our magnitude or strength of R is going to be artificially inflated, or it's going to be artificially higher than it should be. And so that is sort of the downfall of this discontinuous distribution that we have to be careful about. And finally, when we talked about factors influencing the size of R, the fourth factor that can have a misleading or false impression on the R value is when we measure or when we collect our measures in an unreliable fashion, when we have poor reliability. If you recall from your research methods courses, two of the key things about conducting good measurement in research are reliability and validity. Now, validity, which we're not talking about right now, but validity was all about accuracy. Are you truly getting at what you want? Are you truly measuring the construct you hope to measure? Whereas reliability, in many ways, is about consistency. Are you consistent? Now, some of us may be consistently bad in our behaviors, but at least we're consistent, we're predictable. Other people are consistently on time or consistently late. Or things of that nature. But if somebody's consistent, you can at least, there's a predictability to them. Well, one of the bad things with measurement is when you have poor reliability or when you're inconsistent in how you measure things. Now, why is this? Well, this is because in one situation, you may be trying to measure somebody's intelligence or somebody's weight or somebody's height. But if you're inconsistent or have poor reliability, sometimes you may overmeasure them on that factor. Sometimes you may undermeasure them, and sometimes you may get it right on where you're supposed to get it. But what happens is with poor reliability is that tendency to sometimes overmeasure a trait, sometimes undermeasure a trait, it tends to create this sort of ballooning out effect, where the more that you are undermeasuring here, overmeasuring there, undermeasuring here, overmeasuring there, your observations, not only are they not accurate, but they're also inconsistent. So you can imagine what you start to see is sort of a spreading out of scores. So let's take a look at our two scatter plots. On the left-hand side, this would be an example as if we were very reliable or consistent in how we measured our particular values for variable x. And we see a nice, tight, positive slope. So we'd probably have a pretty decently high magnitude R value from that. But on the right-hand side, what we see is when we have the lack of consistency, when we are unreliable. So here you notice, if you look at the right-hand side sort of cluster of dots, they're more ballooned out, spread out from the straight positive sloping line we might imagine that we could draw through there. So the dots are no longer as tightly clustered about that positively sloping line, and that leads to a lower value of R. And how does it occur that they're ballooned out like that? Well, as I started with, because for one person, maybe you overmeasured, say a variable X was weight, and you had a scale or something like that. And if, I imagine most of us have at least once in our life stepped on a scale, either at home or at a doctor's office or in a friend's house, and gone, there's no way this thing is correct. And so, trust me, poor reliability, inconsistency is out there. So let's imagine going back to our right-hand scatter plot. So if I happen to undermeasure somebody's weight in one case and somebody else comes in the next day and I tend to overmeasure and then I undermeasure and overmeasure, what I'm doing is I'm ballooning out my observations because they're not as consistent. And what that does is it leads to what we see in that right-hand scatter plot. So I'll let you be the judge of this, but I imagine you can probably guess where we're going with this. When you have reliability, like good reliability, you tend to have an accurate measure of association. But when you have poor reliability, when you have inconsistency in your measurements, what you tend to see is an artificially lower magnitude value of R, meaning an R value that is closer to 0 than it should be. So the takeaway from these things, we've talked about 4 different factors that can give you misleading values of R. And 3 of them, sort of if you're trying to think about how do I memorize this, 3 of those 4 factors produce artificially lower magnitude values of R, and only one of them artificially increases the magnitude of R. So, give you a second, think about it in your mind, okay, which ones did he do? So, I'm going to give you the answers right now. One of them you're looking at. So which 3 factors give you artificially lower values of R? Well, the first one we had was when we had that if we have a curvilinear relationship, so if our relationship is not linear, if it deviates from that, we're going to get an artificially lower magnitude value. If we have a truncated restricted range, we're going to get an artificially lower magnitude. And if we have poor reliability, we're going to get an artificially lower magnitude value of R. The only of the factors that lead to an artificially higher magnitude or an inflation of the magnitude of R was factor 3, when we had that discontinuous range of values. The next step that we need to look at is something that has become more and more of a trend in statistics, which are measures of effect size or measures of strength of association. So as we get in the next couple of weeks, we'll be moving into inferential statistics. And when we get there, we're going to talk about p-values and statistical significance and power and type 1 and type 2 errors and things of that nature. Well, those are all good, but people don't just want to know, do I have a significant outcome or significant finding? They also want to always have that second thing. Well, how strong was my finding? How strong is the association? Well, so with the R, we get the luxury of starting to be introduced to one of the first measures of strength of association. And this is called R squared. The fancier name of it is called the coefficient of determination. So R squared, or the coefficient of determination, the good news is it's very easy to compute. In fact, the name kind of gives it away. R squared, right? So some of you may already figure out how to compute it. Okay. So, but what does it tell us? So we already know that R. What was R? Let's remind ourselves. R was that Pearson correlation coefficient. R ranges from -1 to +1. R tells us whether or not we have a negative or a positive association between 2 quantitative variables. The closer that R is to either -1 or +1, the stronger the association, right? So, and we know that R measures linear association. So we know all that. But simply by taking R and squaring it, we can find out the coefficient of determination. And then what we see here right now in italics is what I like to call canned language in statistics. And I'm sure I've mentioned this before in previous lecture, but it's going to be another one that sort of comes up as we go through. And so you just sort of get used to the canned language, and then all you have to do is get used to it and then insert the names of the variables and the values you get to interpret it. I think we talked about it a little bit in the past when interpreting the standard deviation. So here's our next round of canned language, canned statistical language. So R squared tells us the percentage of variation in Y that can be explained by knowing X. What the heck do I mean by that? Well, imagine variable Y, usually our outcome variable, is going to have variation, right? Whether it's exam score, whether it's a measure of self-esteem, whether it's a measure of physical strength, whatever the variable Y happens to be, when you look at your sample, not everyone is going to have the same value. There's going to be variability. Well, how do I explain that variability? How do I explain why this person was stronger this person was weaker? How do I explain that this person got a better exam score, that person got a lower exam score? How do I explain that variation? Well, I can start to introduce other variables that might be associated with that outcome variable and measure the strength of association. Here comes variable X. It may be some other variable that explains why I see variation in variable Y. This R squared allows us to quantify or get an objective number to capture the strength of association. So let's take a look at an example. Let's say that I collect data for a group of students who have taken my statistics class and have gone through the midterm. And I want to see, is there an association between the hours spent studying, right? That'd be variable X, and how well they did on the midterm, their score on the midterm exam. That would be variable Y. So once again, I'm looking at the association between variable X, hours spent studying, and variable Y, the score on the midterm. And I think most of us would probably predict or hypothesize that those individuals who spend more hours studying are more likely to score higher on the exam. And people who spend fewer hours studying are likely to score lower on the exam, right? So we predict a positive association between these two things. So let's say I go out and collect data from a sample of individuals and I get this R value that I see listed on this slide. I get an R value of 0.70. So it's a positive value, and when we think about the range of possible R values, 0.70 is not too shabby, right? It's getting closer to that 1. It's definitely not close to 0. So we're thinking like, okay, I'm seeing an indication of a positive association between hours spent studying and score on the exam. So what can I do with that R, that 0.70, to give my readers just a little bit more information and a little bit more statistical knowledge about the association? Well, I can compute the coefficient of determination, aka R squared, aka the strength of association. So all I have to do is take my R value, 0.70, and square it, R squared. So I enter that into my calculator, I get an R squared of 0.49. Now that R squared of 0.49 gives me something that I can nicely interpret for my audience. How do I interpret it? Well, I use that the bullet point that's in italics where it says percentage of variation in Y. That can be explained by knowing X. So how does that look? It looks like this. I take that canned statistical language of the percentage of variation and I apply it to my variables which were hours spent studying and score on the exam, and I introduce the actual value I got for R squared. So translating into that language, I have approximately 49% of the variation observed in midterm scores can be explained by the number of hours spent studying. So thinking back to our canned language, I started off with the percentage of variation in Y. What was Y? That's our outcome. That was our midterm scores. And then can be explained by X. What is X? X was our number of hours spent studying. So that right there is a very useful tool that also makes it nice to present to an audience. It's something that they can wrap their minds around, even if it's sort of in an abstract sense, to understand that 49% of the variation, this is, a pretty decent amount, half the variation in midterm scores are explained by how much you study. But one of the things, the next obvious question, and somebody in the audience would raise their hand and say, okay, well, 49% of the variation in midterm scores can be explained by this thing, hours spent studying. What about the remaining 51% of variation, right? Because there's always 100% of variation. Well, that 51% of the variation, the unexplained stuff, is going to be due to or caused by other factors that we haven't measured yet, unmeasured factors. And this is kind of what we do with research, right? We start with, okay, if I want to explain crime, if I want to explain drug use, if I want to explain success or failure on something, I start to look for things, factors, variables that might be associated with it. And that's what we're doing here. So we realize, okay, we've got one factor, one variable that seems to have contributes a lot to how well people do on the midterm, but there's still quite a bit of variation that is left unexplained. And that's where we encourage other researchers to go out and say, hey, so let's go find out what are those other things out there in the world that would explain this other 51% of variation. Finally, as we wrap up this lecture about bivariate association between two quantitative variables, I also want to remind us that not all variables are quantitative, right? And even though I've stressed the fact that Pearson's R is sort of the granddaddy, the gold standard of correlation coefficients, there are a lot of other coefficients. Many of them are sort of derivatives of Pearson's R. So the nice thing is, once you understand how to interpret Pearson's R for quantitative associations, moving on to many of these other correlation coefficients isn't too hard because they're sort of explained and interpreted in many of the same ways. But let's just take a glimpse at what some of them are. We are not going to go into great detail in this over the course of this semester, looking at a lot of these other measures of correlation. If we get a chance, we'll touch on them throughout some of our lectures, but I mainly just want to make you aware that they're out there, and also not to be intimidated if you're reading an article and they mention one of these. As I said, more often than not, they're interpreted in a very similar manner as far as how we might interpret our R values, and also even our R squared values. So let's take a look at them. So what we see, these are just a few, and there's more out there, but if both my variables, both variable x and variable y, were at that nominal ordinal, if both variable x and variable y, meaning variable 1 and variable 2, were both at that nominal level of measurement, one of the measures of correlation I might use would be either what is known as the phi coefficient or Kramer's V coefficient. And we will see these in this class. We're going to talk about chi-square tests later in this semester, which are designed to examine association between two nominal level variables. And when we want to get a measure of strength of association, we'll look to phi and Kramer's V. If you're looking at where you've got one of your variables is at the nominal level of measurement and the second variable is at the ordinal, you might consider using what is known as the rank biserial coefficient. If one of them is at the nominal level of measurement, the second is at the interval, you might consider using what is known as the point biserial coefficient. This is one that's often associated with t-tests. And so T as in Tom, that is. And so when we talk about t-test, once we get to inferential statistics, think about that would be a time where we could use the point biserial correlation if we wanted to measure correlation between those two variables. If you have two ordinal level variables, you can look at Spearman rank. This is a pretty commonly used correlation coefficient in quite a bit of research. And then finally, when you have both variables are at that quantitative level, meaning they're both at least at the interval level of measurement, that's where our Pearson R comes into play that we've been talking about. So I'm not going to go into any more detail about these right now, but I just wanted you to be familiar that they're all correlation coefficients. And as I've stressed repeatedly, oftentimes once you understand how to interpret and understand Pearson's R, understanding these other types of coefficients isn't that hard. It's just knowing when to apply the proper type of correlation coefficient given the level of measurement of your variables. So we'll end it there. Have a good day.